Let's talk about cyanonucleophiles. Nucleophile reactions with aldehydes and ketones. So I'm going to go ahead and just start off like I always do, giving a generalized overview. My carbonyl compound there. There's my R prime. Could be a R group or it could be a hydrogen. I don't really care. And I go ahead and react that with sodium cyanide and hydrochloric acid. And my product is going to be carbon there, prime, oxygen there. The unique species known as a cyanohydrin. Now, obviously, what we have here, I don't know if you noticed, is this is a base, the cyanide is a base, and this is an acid, so it's kind of going to give us some interesting products. Keep that in mind whenever you see that acids and bases don't always match up and just stay in that configuration. So let's just draw the actual mechanism behind that of what we're talking about. First step is always going to be the nucleophile attack. So being a nucleophile, it does the exact thing that we always expect nucleophiles to do and go ahead and reacts there. That's nothing new. It's an oxygen with a negative formal charge. And just like we said earlier, this is a base, this is an acid. Well, that's going to go ahead and react. And that negative formal charge isn't going to stay there for long. It goes ahead and steals a proton from this hydrocyanic acid, giving us a final product, giving us a cyanohydrin. Cool. Alright, so the next reaction that I wanted to talk about is sometimes called a witting reaction. And I'm going to go ahead and write that out. Just like before, I'm going to give a generalized overview and then write out the details of it. So you start off with some type of a compound, and you'll understand why I'm drawing it like this later. But here's an aldehyde or a ketone. Again, not really playing favorites here. And I go ahead and I react that with a unique species that I haven't seen at this point in the course up until now. It's 3 phenyl groups attached to a phosphorus that is attached to a carbon that has 2 other groups attached to it. Now, what's interesting about this is that the phosphorus attached to the phenyl groups has a positive formal charge, and the carbon, well, those are lone pairs, so obviously it's a carbanion. And anytime you have a species like this that has a full octet, which both of these do, and contrasting formal charges right next to it, we call this a yide. This is a very interesting product. And so what we get out of this reaction is, I'm going to keep my colors to show that where these sources came from. So there's our R and our R prime. Attached to that is going to be the carbon group. So you formed a carbon-carbon double bond. That's a plus. The other thing that we're going to be forming is, and sometimes organic chemists list this as a byproduct because it doesn't, we're not really interested in it, but you end up getting that species as well. This is obviously the main thing, though, is that you can form an alkene and think of all the types of reactions that you can do with an alkene. But let's just real briefly talk about the synthesis of our reactant. So I'm going to bring that down here. Just 2 steps to it. The first step, and I'm going to make a note here that this is as an SN2 nucleophile attack. And I'll explain what I mean in a sec. Compound there with 3 phenyl groups attached to a phosphorus, and also we're going to head and react this with some type of a alkyl halide. Now, it cannot be a tertiary alkyl halide for reasons that I'm about to explain, but I'm going to go ahead and just make it a primary, just because who cares? It's a SN2 nucleophile attack, so obviously that should kind of lend itself. Don't forget that those are vital, tools to know. And it goes ahead and does just your stereotypical SN2 reaction. We also have our halide floating in our reaction mixture as well, so we sometimes call this a phosphonium salt, but that's not really so important. So it's just the next step in our reaction here of synthesis. So first was SN2 nucleophile attack. The next one is going to be deprotonation. Have is some type of a base. Never really specifying the type. There's all kinds of it, but just know that this base is a very strong base. Why? Because it's going to be deprotonating an sp3 hybridized carbon. So let's draw our reaction arrows there. So we have successfully finished our reaction. We've yielded the product that we're looking for. Now, although this looks goofy, know that obviously this is the minor resonance structure for this species. I can more, if I wanted to at least satisfy my formal charges a little bit better, I would move this electrons in to form a pi bond. But it's always the minor resonance structure is what determines the reactivity. So I don't really see a reason to draw this as in the major form, but just know that that's the reactive species. Now I'm going to clear all this up, and then I'm going to draw a detailed step-by-step mechanism of this initial reaction here that we just talked about. All right, so the first step is for our nucleophile to come in and form a four-membered ring. And obviously, if you're forming something that unstable, that's your rate-limiting step. But what we have here is, there's our carbon there. Going to designate that as R prime. Remember, that means that it could be a hydrogen or an R group. I think that's hopefully the last time I'm going to reiterate that point there. But reacting in this as well, and I'll go ahead and do it in blue color there, is my iode. Groups attached to the phosphorus. So, in a concerted reaction, the carbonyl, or the carbanion reacts with the carbonyl compound. And whereas instead of coming up here and moving away, that negative charge that we're going to form, that now has some place to go. So that negative charge of the electrons is being attracted to the positive charge of the phosphorus. And this is the rate limiting step, obviously. So I'm just going to draw that here, that's your rate limiting step, forming a four-membered ring. So this is called an oxophosphentane, and as you can tell just by looking at it, it's a four-membered ring. Four-membered rings being, just by the way that they are super, super unstable, and they're not going to stay in that conformation for very long. It's kind of interesting. I sincerely doubt that they were able to isolate this. But anyways, the next step after that is, and I'm just going to go ahead and I'll write it over here as number 2, is elimination. Essentially of the byproduct that I'm not really that interested in. And so what's going to happen here is these negative the strain in this ring is going to get to the point where it's not going to be very happy, and so it's going to move to a more stable configuration. That moves there, and in the same way as a concerted reaction here, it is a concerted intramolecular reaction. What I get out of this is, go ahead and draw the forward arrow there, a carbon. Okay, so those are my products of my reaction. But the only one, I'm not really that interested in the triphenyl phosphenoxide. What I'm interested in is the fact that I've formed an alkene, and that's something that you should take away from this. But very interesting reaction that we have an intramolecular removal of, or just I guess breaking, I'd like to think of it, of a four-membered ring, and the fact that we can even form a four-membered ring in the first place. Very impressive reaction, pretty cool. Props to the guy who created it, however long ago that may have been. So the next thing that I wanted to talk about would be using this as a retrosynthetic analysis of this. So last thing I want to talk about for the witting reaction. So there's really just two options you can have, I guess, when you're doing this. So the first option that you can use is to simply just consider the nature of your iode, or your reactants there, and how this is going to be, I guess, created and then in resonance of where this came from. And the significance of this is, remember that this was made by an SN2 reaction. So you would want to compare that and know that with SN2 reactions, don't forget that the big obstacle of SN2 reaction is the steric hindrance. So when you're looking at compounds and you're trying to determine, well, okay, which one of these was my iode and which one of these is the carbonyl compound that I was using, think about the production of this, how this would have come about, and then that will kind of give you, I guess, lead into itself of where things came from. That's all I wanted to say about that.